Okay, folks, so now what we're going to do in this video is crazy fun. Some of you watching this are going to get turned on by this and like theoretical computer science, and some of you are going to say, forget it, it's for the birds. But I want to expose all of you to this a little bit because, again, from a cybersecurity perspective, you should see some different angles. Now, you recall, we talked a minute ago in one of our previous videos about the idea of an overt and covert channel being different, right? That overt is something you intend. Covert is this shared thing where I can signal someone. Now, I'm going to posit some systems that I'll create that are kind of theoretical. It's due to some work by a guy named Bell-LaPadula in the 1990s, very interesting researcher who's trying to come up with alternate ways to think about disclosure and integrity properties in a computer system for cybersecurity. Here's what he came up with. Now, I'm going to pop up a chart here. You'll see something we're calling System Y. And on the left, we've got a user, user A, and on the right, we've got a user, user B. And the way this dopey little system works is that A sends a bunch of messages to this system, System Y, and then at the end of sending a bunch of these messages, the parity or odd or evenness in the number of messages that were sent is sent to the user B. Got it? So I go boom, 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 and then we add up how many of those there were. If it was odd, I send odd. If it's even, I send even. And I think you would agree, A can certainly signal B, duh. If I want to do an even number of stuff, I do that, I send you even. If I want to do an odd number of stuff, I do odd, I send you odd, and you're getting odd or even. We can come up with an X bit per second covert channel, or microsecond, or millisecond, or whatever it is. You follow? But now if we look at, I'll throw a chart up here that's going to show you the system itself introducing randomly generated messages. I have it shown as a 0 popping out from the system. So we're going to make the zeros and ones be the inputs that are coming in, and then some random thing the system does, and then the parity that user B sees is going to add up everything, not just what user A does, but what randomly the system does as well. It's noise. So I want to send even, but the system generates some noise. Let's say it's odd. User B is going to see odd. Or let's say I want to send odd, and the system generates odd as well. Odd plus odd is even. User B is going to see even. I've closed the channel. Do you see what I mean? There's another example. I send one message. I send a 1. The system sends one output randomly, a 0. 1 and 1, that's 2 things that were sent. It's even. I'm not adding the 1s and 0s. I'm adding the number of messages that are being sent. Do you follow? I would claim that this system Y prime, we changed Y to Y prime when we added the noise, is called deducibility secure. That's the definition that was introduced, meaning A can't signal B in this example. And that's a property that we look for in something called information flow theory. So instead of Bell and LaPadula, who can read, who can write, we say, is it possible for A to somehow signal B? Can I have information flowing from A to B? Don't worry about whether you've got TCP packets going this way or that. Forget all that. I'm interested in information. And I think it's a better model. So we can see this system Y is clearly deducibility secure. Let's look at another example. And this one I've drawn a little funny. I put the user down on the bottom and saying user A can't even signal this system Z or Z. We'll say system Z. User A can't do it. There's no way of signaling the system. But then randomly from somewhere, inputs and outputs are hitting the system randomly. No input from A. And then B just sees the parity of the random stuff that's hitting its system. Clearly, and I'll show you in the next sort of diagram here, you can see that system Z clearly is deducibility secure, right? But it's sort of obvious given the fact that A can't signal B. Do you follow? These are 2 examples of systems that respect a property that's focused on closing covert channels. And we did it in both cases by introducing sort of crazy noise property. Bell-LaPadula did it. And you're going to see in a subsequent video, we're going to put these things together to see what happens. You're probably wondering, why is Ed showing me these weird systems? But once we hook them up, you're going to see an interesting property come up. Now, just to make sure we're all together, let's do a little quiz here as we do on many of our videos. And the answer is obviously C. C is the definition of an overt channel. So I think you probably have a pretty good understanding at this point of these things. Now in a subsequent video, the next one, we're going to hook these things up and I'm really going to knock your socks off with that. So we'll see you in the next video.